I'll get that recording started. Thanks everyone for joining us. I'm really excited to be hosting this seminar with Alex Reinhart. Alex is an associate teaching professor of statistics and data science at Carnegie Mellon University, where he has taught statistical computing, regression, and applied data analysis courses. For 2 years, he worked with CMU's Delphi group on COVID-19 response. And this included a period as co-leader of its software engineering team, where this involved coordinating numerous PhD students, faculty, and also professional engineers developing data and forecasting pipelines. So we're really excited to hear his presentation today, which is Git for the Unafraid, what they didn't teach you in Intro Git. And I'm really happy to be hosting this webinar with the Maynard user group. Thanks, Donald. And also to have funding for this seminar from the Henry David Thoreau Foundation. And I'm Lori Baker. I'm a math professor at Bates College in Maine. And so we're really excited to have Alex here. We'll have the presentation and then there'll be some time for questions at the end as well.
All right, shall I dive in?
Yeah, go for it.
All right, so I'm going to turn things on here. So hopefully you all can see the slide set up here. And I'm also going to switch back and forth to a terminal. Let me move everything around. Switch back and forth to a terminal to show you some things. So the subtitle of this talk is What They Didn't Teach You in Intro Git, and I have a model of sort of what students learn when they start Git based off of my experiences having taught some courses for our graduate students here. And so I'd like to teach sort of the extra steps. I'm going to assume a little bit about knowing about what Git is and version control and committing changes and things. And we're going to talk about things like collaboration, working with other people using version control as a tool. So I'll dive into it. If you do have questions during, COVID gave me practice working with the Zoom chat on the other screen. So if you have a quick clarification question, you can just throw it in there. Otherwise, we'll try to have some time towards the end. And I'll just jump in here. So let's talk about version control just briefly about what it is and why we're doing it, and so on. The thing you run into with whatever project you're working on is they expand and to involve a whole bunch of stuff. You have your code that you're working on for your data analysis, your data pipeline, or whatever it is. And there's the data files you're loading in, there's the output, and there's all the plots and tables you've made, and the configuration and the tests and the what, a whole bunch of junk that'll inevitably come out of whatever project you're working on. And that will start to get unmanageable to deal with. And particularly with the history of the stuff you're working on, and keeping track of what you have done. Because if you could keep track of what you've done to everything, you can do things like collaborating with other people without making conflicting changes. And I don't just mean like you just put the files in Dropbox and now you all edit the code at the same time. That violates the conflicting changes part of this, because you could be both editing the same thing at the same time. If you can keep track of changes, you can compare what you did and what someone else did and figure out how to merge things appropriately. You can also do things like try something that you're not sure will work, and then get halfway through, a day of writing some code and rearranging everything, and then realizing that was a bad idea. And instead of just leaning on your undo key, if you have the history of all your changes, you can just go right back to where you started, where you were before without worrying about it. You can also mark points in the history. I use this a lot for things like I write code that I'm using for a paper I'm going to publish. I submit the paper to the journal, and then I'm working on the code for some other stuff. And 3 months later, 6 months later, the journal comes back and they're like, actually, we want you to change figure 2 and color code it a different way. And well, I've changed my code since then. I've been working on things I can't generate. So I can go back to the version I had and make figure 2 again, but whatever what they want me to change. Or a very common problem that students in a 1 semester course do not appreciate until it happens to them, trying to figure out why you did that one thing you did 6 months ago. You go back to your code and you look at your code, you're like, wait, what does this do? Why is this here? And if it's a collaborative project, you'll be like, what idiot put this here? And then you go to your version control and the idiot was you 6 months ago. And then you can see what you changed at the time to try to figure out why you did that and what that code is for. And you'll be able to help figure out problems that way. And I'll talk more about making that easy for yourself. You can also do things like, I swear this worked last week. Why doesn't it work now? Well, you can see what you changed since last week and figure out what you did that broke it. This happens a lot when your script involves lots of parts, and so there's a thing you're working on now, and it still works, but something else stopped working. And, what did I do? Well, you can look back at the history of changes and try to work that out. And this is what version control is for, is doing all of these tasks. So I have used it in a lot of places. I've released R packages on CRAN that I used version control for everything. Lori mentioned in the introduction, working on COVID data processing. We built data pipelines that large teams developed. And so we've worked on a project with 10 or more people all committing code to the same thing. I use it to track lecture notes and assignments for some of my courses and the changes I made to those. Data analyses that I'm working on with a group. Someone's like, oh, I added a new plot to do a thing, and someone else can add a new model, and you can all work together on it. Have used it for things like the source for manuscripts, papers we're writing in LaTeX or Quarto or whatever your favorite format is. So someone can work on section 2 while someone else adds the new table to the appendix or whatever issue. And even things I do myself that nobody else is ever going to look at, once you get the habit of version control, it just feels wrong not to use it. So I use it anyway. So let me give a brief recap of Git as the version control tool before we talking about some of the more collaborative features that are less well known. So Git is the most popular version control system. It was designed by and named after Linus Torvalds. That is his joke. He named it after himself because he is, well, fill in the blank. Git is primarily a command line tool, but as we'll see later, you can use it from RStudio or from fancy editors and other software. And Git involves repositories, which is just the directory full of files that it's tracking when it's contained to that directory. And what it keeps track of is snapshots of the repository at specified times. Here's what it looked like now, here's what it looks like now, and then that history is available for examination. It is distributed, meaning you can send a copy of your repository to other people, and then they can work on it and have their own history and then share changes with you. You can send changes to them, and it can interoperate. The problem is that Linus Torvalds, was a serious programmer, developed this in 2005 for Linux, also named after him. And it's designed for, well, put it this way, it's not the most user-friendly piece of software in the world. And so most novices tend to take an approach of learning out of this book here on the right and just memorizing 6 things in Git and then not touching anything else because something might break. And I've seen this with our students. We have them use Git in the course, something weird happens, and then they never want to touch any of the Git features. They want to avoid it as much as possible until they have to turn in their homework. That's a problem. So we're going to try to get some of the concepts so that we can do this. So we can create a repository in a directory that we have where we already have some files in with git init. And so here I'm showing a sample shell, but I can also just switch over and show you an actual shell. I have a folder here that contains a couple files, one of which is this R script you see on the top, which is the most evil R script I've ever written. And I can just do git init, and it says that it's made an empty Git repository in this directory. And if I look at the directory, nothing much has changed. Same if I look at the directory here, it's just a couple files, nothing special. But what Git did is it made a hidden folder, this one, that contains information about the snapshots of the history. And we're going to see stuff happen with that later as we go through this. So we have a repository with some files. I've initialized it, but I have not yet actually made any commits, that is, any snapshots, and it's not tracking any of the files. We'll talk about that in a moment, but it's not recording changes anything yet. So what I need to do is make a commit, which when you commit, you're making a snapshot recording the current version of every file. Each commit has its unique identifier, which is a hash. It's called the commit hash, which is based on the contents of the commit. And every commit is linked to its parent, the previous snapshot. So if we make a commit, then I make some changes and I make another commit, the new one will point back to the previous one. And what I mean is this. We'll look at just the top half of this for now. On the left, this is, say, the first commit. And these hexadecimal numbers here would represent the commit hash. We'll see some real hashes in a moment. And so I make a commit, I record the current version of some files. Then I make some changes and I make a new commit recording the current version. And that could be this one. And it has a pointer back to its parent. Then I make a new commit and then I make a new commit. This is the history. Now these commit hashes are annoying to deal with because they're long hexadecimal numbers. So A, we can abbreviate them as we've done here. And B, there are human readable labels. The commit that I'm on right now that I just made is the head. And it's also on a particular branch, which is the main branch in this case. Those are both names for this commit. And we'll see in a moment that you can in fact have parallel histories like this one I'm showing here. We'll see that in a minute, but for the moment, we can just look at this top history here and see that we can make changes. Now, Git does not record the changes automatically. You have to add things and then make the snapshot. And instead of telling you about it, let me just show you. So we did git status, and we saw I can then add a particular file. Git status will show that change is to be committed. The other changes will not be. So this is not really a snapshot. It's a selective snapshot. I choose which changes to include. So if I now do commit, oh heavens, if I do, we'll pretend that didn't happen. If I do commit, I can, which I tested this immediately beforehand, so I don't know why it didn't work, but never mind. If I want to do a commit, I need to specify a message because with every message, I record what I did with a label. So I might give a short message. Here, I'm going to do it at the command line because the thing that pops open in editor isn't working right now. And I might say something like, this is the initial commit because there's nothing, all I've done is add the initial file, so there's nothing really to say here. So it indicates this is the commit hash. This is the name of the branch I'm on, which is main by default. And it says it made one file, inserted 38 lines. It created this file, a little summary of what I did. So I've added that file. Now, some things in my repository I don't need to track, and I don't want to track changes in. So we might have noticed, for instance, if I ask for git status again, it mentions this ds store and this rproj user. Ds store is something Macs make when you view a directory in Finder. It keeps track of, like, did you view it in list mode or in thumbnail mode or whatever, and it stores all of that junk in this file. So there will be one in every folder you have, and you don't care about the history of it. That's just the history of how you viewed it. This rproj user thing is from RStudio. When you make a project, it stores like your workspace and other junk in there. That also you don't really care about the history of. You can also imagine if, for instance, you're using LaTeX and it makes all those files, it dumps out the log file and the aux file and whatever, like who cares? You don't need to track that. You just want to track your tech source code. Or, for instance, the R history file that R makes when you run it of all the commands you've run. You don't want to track those, it's just wasting space. So what do? We can create a git ignore. So a git ignore is literally a file named .gitignore, spelled correctly. And in it, I can write things like .dsstore or say if I'm doing LaTeX stuff, ignore the log files. So each line contains a thing I would like to ignore. You can do it either name the file, name a directory, or here with the star, I'm doing a wildcard, so I'm saying anything ending with .log. And if I save this file and I go back to my shell, dsstore doesn't show up anymore because Git is pretending it never happened. So creating a git ignore is a useful thing. I will mention, and I'll come back to this package several times, there's a package called use this that will automatically create a dsstore for you, or create a git ignore, sorry, for you with all the common junk that like our projects will have and ignore all of them automatically. I do see a question about ignoring dsstore in all subfolders. You probably can do that, for instance, like this. Star star as a pattern for directories. Something like that should work. And you can ignore it all. You can also create a like global git ignore git configuration for your whole machine and always ignore it. I would say though that you probably want it per project so other people with your repository ignore the same things and don't accidentally commit things. Um, and these tend to be painful because when you do accidentally commit them, then every time you make a change and you do git status, those files show up because they changed now and you're like, well, I don't care about them, and you accidentally commit the changes and just clutter everything up. So git ignore is an important feature. Another is writing commit messages. So I made a simple one there, but you can write a whole bunch of stuff in a commit message, and you should. So I printed out a commit message for an R package that I worked on. Notice when I printed it out, it shows the commit hash, which is quite long. It shows who made the commit, the date that it was made, and it shows a message that's actually long enough to scroll here. There's a standard style. The first line of a commit message should be a one-line summary. That's because if we print out the log of changes, this is what'll be shown, so you can have one commit per line with the summary. You then leave a blank line, and then you can write multiple paragraphs of additional information about why you made the change. And I do that because if I want to come back 6 months later and be like, why did I change this? Why is this code here? If I come back and I see this commit, I can see the commit message and I can know what I did and why I did it. And other people working on the project, if I'm collaborating, will know why I'm making changes. These commit messages get used, as we'll see later, when we're doing collaboration and we're sending changes to other people to ask them to include them in the project. They can read these commit messages to know what I'm doing and why I'm sending them this code. So like open source projects, for instance, tend to be very detailed about wanting good commit messages. I see a question about using LLMs for composing detailed commit messages. I have not tried that actually, although I'm sure there's a tool that will do that for you automatically now. I would say though that remember the audience of your commit message is you 6 months from now or your colleague sometime from now. And so rather than, for instance, describing everything you did, you want to describe what you did and why you did it, particularly the why. And the why context may be hard for an LLM to know if you just show it, here's the code I changed, write a commit message. It doesn't know why you needed to do that. Because if the context is like, the people providing the data changed the format and they added this column and they sent an email explaining like all of that stuff, if you can put that in the commit message, that'll help you understand the code later versus just saying, we changed this part of the file to add this column. Like, but why did you do that? So you do want to try to include context on what you were doing. I mean, if you're doing like fixing a typo, like you fixed a typo, you don't need it. Doesn't need to be Tolstoy in here. But if you're doing fixing a difficult bug or something, you do want to have a good message for that. Once we've done that, we can use git log to see commits and see details of each. And to do this, since we've only made one commit in this repository, on the top here, I have a different repository. And I will, this is a R package that I've been developing with someone else. And I will do git log here. And we'll see that it lists a bunch of commits that I made, and I can jump down through here through me fixing a bunch of stuff. As for some of them, I just don't give much of a message. But then like here, I've explained why this is a problem and why I had to change it. And if we jump far enough, you'll see my co-author, some of his commits. So git log shows all kinds of, all the history going back as far as it goes. And I can have it show me any one of those commits. So if I'm like, what do you mean fixed column name documentation? What does that mean? Well, I can take that commit ID, any prefix of it will do, and do git show, and I get something like this. And let me talk about what that is. That is a diff. A diff, difference, but it's always called a diff, shows you what has changed. And diffs come in a format. Here we see it's showing the path of the file. It's showing where we are in the file. And then it shows with a minus sign in front things that were removed and with a plus sign things that were added. So you can see what I changed in that commit, but here in the color-coded format, you can see even better. This line was deleted, and these new lines below were added because they have pluses, they're color-coded. And you can see that for all of the changes that were made in that one particular commit across all the files. So another feature, you may have made commits and so on, but you should know that Git knows if you've been bad or good. You should know about git blame. Git blame answers a common problem. I've hinted at the looking at some code and being like, wait, where did that come from? Who made that change and why is it there? That's what git blame is for. Git blame shows you who last changed each line of code and what commit they did it in. So if I expand this a little bit, and I pick a file in this repository and I ask for git blame, let me shrink this here. It shows me the file on the right, and on the left, in this column on the left, I see the commit each line was changed on. And so you see, I was the last person to touch a lot of these documentation lines, but we jump down and we see my colleague was the last one to change these lines. And we have the commit hash of the commit that changed them. So if I come in and I'm like, wait, why did we check, that there's factors less than one? Why is that important? I can come and look at that commit and see if there was a message explaining it or tests or other changes that tell me why that was done. So the name git blame, is implying that the sole purpose is for me to go tell my colleague like, hey, he did it wrong. That's not the purpose of git blame, really. The purpose is to be able to look through the history and understand what changed something so you can figure out why, or if there was a bug created, like, okay, what were they trying to do? What did they do wrong? How do I fix it? So you can go back and investigate things like that. So we have those tools. We also have tools for creating parallel histories. Basically, Git, in every time travel movie where they start talking about diverging timelines and how, you can't go back now, there you could model a lot of those using Git. So let's see how we do that. A branch in Git is a separate line of history, and each branch has a name, and that name points to a commit and its parents. And we can have many such branches in one repository. What do I mean? This repository started with one commit. We made another commit, and then it diverged. Someone made a branch named experimental on which they made a change, and they made another change. But someone else on the main branch made two changes there. Now these are two different snapshots of the repository that look different, have different changes in them, and we can switch between them just by telling Git I want to look at one or the other. And I can make changes to one of them and make new commits and then switch to look at the other one and use that for lots of things. So I might do this for a lot of reasons. One is try to make some changes I might throw away. I might be like, hey, I have an idea for a much faster algorithm here. I'll make a branch. I start making some changes. I change one function. I commit it. I update the algorithm. I do a bunch of stuff. And I get 6 commits deep when I realize it'll never work. Well, now I can just switch back to the main branch and just pretend that never happened. You might also do something like, if you're releasing software, you might have a release version and a development version. That is, you work on your code for a while, you make a commit, this is the version I'm going to release, you release that, and you make a branch at the same time. Then you go along adding new features and doing new stuff on the main branch. When someone emails you and says, hey, there's a bug with the software you released, you should release a new version. You're not done with all of the new stuff you were adding. So you go back to that released version, you branch from there, fix the one thing they complained about, and then release that version. And then you can switch back to the branch where you were adding a bunch of new stuff and keep adding all the new stuff and making the changes. And whenever you need to fix one little thing in the released version, you can switch back to that. Pretty much every long-term supported software by major companies uses this kind of model. They have a release branch and they have a development branch. The release branch has the bug fixes. The development branch, they keep working on new things. That's a very common model. We can also use this in a collaborative project where everyone works on a branch. There's a main branch. I make a branch. I work on my things. When I'm ready, I propose it to be included to main. That is, I say, here's my changes. I think we should merge these and include them in the main branch. Meanwhile, someone else in another team has been working on other changes on their own branch. We don't interfere with each other. We just merge the changes together at the end, and the main branch has the finished version of everything. To take this to an extreme, at Google, every Google product except ads is in one repository, one thing, and every software engineer is making their own branch to change add the new feature or whatever it is they're doing, and then submitting those to the one central repository to be included in the branch that then is visible to the world. So that amounts to being able to work on a project while other people are changing the same stuff. That is what branches are for, so we're not trampling on each other. So we can make branches explicitly. So let me switch back to our demo repository. Yeah, I can say make a new branch. And if I look at my status, I'm still on the main branch. I haven't actually moved. I just made a new label. And it might help if I look at my log, we'll see this most recent commit is the head of the main branch, and it is also what new branch is pointing at. So these two branches are the same right now. But if I do git switch, now I am on that branch. If I make a change and commit it, it will have that label instead of being labeled main. I see question about switch and checkout, which is a good question. So if you learned Git more than, I don't know, a few years ago, you learned to do Git checkout. Git checkout can do like 17 different things with a whole bunch of different flags. And so it gets confusing just because people use checkout to do all these different things. So they added Git switch. All Git switch does is switch branches. Actually, they probably added more things to it since then, but all it's supposed to do is just switch branches. So it's the easy way of doing this without getting confused in a tangle of options. So I am on this new branch, and I'd like to show you something. So if I switch back to my code here and I make a change, and I make a change there, and maybe I delete something else, and whatever it is. If we do get status, we'll see I've modified that file, and so it shows that file's been modified, and so I can add it. I can make a commit. Now I have, notice it shows that this is on my new branch, which shows me what I did. Now, watch what happens when I do the following. My file changed. The changes are gone. When you change branches, Git literally changes what's in the folder in the repository to match that branch, the most recent commit on that branch. So it all changed. And before you freak out, I can spell it correctly. I can switch back and it comes back and everything's there. I see a question about this on GitHub. I will actually be pushing to GitHub a little later to demonstrate, so it will be. But we've seen how branching works, that I can switch between them. Let me show the log with a little flag here for graph that illustrates main is back here still on the other commit, and the new branch now, there's a little line showing sort of the history going by. The new branch points here, main still points to the previous commit. So I'm going to switch back to main, and we're going to do some additional stuff there in the subsequent steps. So how do we use this to do collaboration? The fact that I can make branches and do things with them. Well, I can push and pull Git repositories from one computer to another. So there's various services that exist to do this. GitHub being the most prominent, but you don't have to use GitHub. There's Bitbucket and GitLab and Codeberg and SourceHut, and there's a zillion of them. Where there's a server where that lets you push your repository to it, or you can just stick a server under your desk and push your repository there. Nobody says you have to use one of these services. And you can do it all however you'd like, but these services do make it easy. And Git natively supports this workflow where you have a remote. That is, before I show this diagram, I guess I'll explain. I have made a demo repository on GitHub for us. It is currently empty. So I'm going to do the following. I'm adding the remote and I'm giving the link to it. Now, Git knows how to send files to that remote, how to send my history and my changes. And when I do that, what I can do is make up what are called tracking branches. So I've annotated it here. Suppose I make a commit, I make my second commit, and I send those changes to the remote server, which I've called origin. That's the default name Git uses when you clone something from a server, because this is the origin of the stuff you cloned. But suppose I'm here and I send all my changes to the server. So now on the remote server, that's where main is. This notation means on the remote named origin, this is the branch named main. Then on my computer, I make a couple more changes. Well, those changes are not on the server. It doesn't automatically synchronize. So instead, I have to tell it to. And there's a few things I can do. I can fetch changes. I can tell it, hey, go look at the server, see what's new, and bring those changes, but don't update my local branches. Just make a record of where the server is now so I can get those changes if I want. I could also pull, which would be, say, for instance, from the main branch, take the remote main branch and bring all of its changes into my main branch. Or I can do the reverse. I can push, take all the commits I made and send them up to the remote. So, for example, I can push main to origin. So it spits out a bunch of mysterious stuff about delta compression, and then it says the main now has a branch, or the remote now has a branch named main. And if I go to GitHub and I refresh the page, we'll see it now shows my file and the one commit I made on the main branch. It does not, however, show the other branch I made, and that other changed because I didn't push that. Now, what happens if, for instance, someone else pushed some changes? Someone else made push changes on main and they pushed them, and then I go to push. They have a history. I have a history. This is the, I went back in time and deleted my grandfather sort of problem. There's two histories that now don't align. Because remember, Git keeps track of this commit came from the previous one. If the timelines don't match, the commits I'm pushing do not come from the commits that are already there. There are two parallel histories. Git will complain and it'll tell me you can't do that. You're going to have to deal with the conflict here and figure out what to do. So what does that mean? That means merging conflicting changes. So for instance, suppose I was working on the main branch, someone else was working on the experimental branch. That could be the same as I was working on the main branch on my laptop, someone else was working on the main branch on their laptop, and then we tried to push them to the same place and they collide. If I do that, I make the commit, they make the commit, and I want to combine these, they may conflict with each other. They may not. A conflict refers to when I change the same place in the same file, so Git can't figure out how to reconcile the changes. If it can figure it out, it's like, well, you changed this file, they changed the other file, so we can have both of them. All it does is it makes a new commit that points to both parents. You see this new commit has two arrows coming out. That is a merge commit that stores the changes, sort of fitting both of them together. If there's a conflict where you both change the same thing, so it doesn't know what to do, it will ask you to decide what to do. You will then edit the file to show the version you want, and then record the merge commit that has that fix. So this leads to a standard workflow. You've got your main branch where you have your final tested code. When you want to make a change, you make a branch, you edit the code, you add your tests, you do whatever, make sure your tests pass, commit your changes, you push those on the branch. Someone else can review those changes. And if they pass the review, they merge the branch into the main branch with your changes. Now, how do you do that? How do you send the code to someone to review? The old school way is to email it. And that's what Git already supports. Git has some commands to say, take this branch, take all the changes, turn them into a formatted email with all the changes so I can email them to someone. Now, that's how the Linux kernel is developed in a few other projects, but you probably don't feel like doing that. So the hip, cool way is to use a service like GitHub or GitLab or one of them, because when you go there and you push a change, there's an interface to review the changes. So in fact, if I switch to that branch I had a new commit on and I push it and I pop up to GitHub, it says, hey, that branch had a recent push. You want to make a pull request. And a pull request is GitHub's term for asking someone to, merge the changes I made. And I put in some description. And when I make it, it shows up with a way of letting me see all the commits that were made and the messages that were made in each of them, and a way for me to see all the changes in the files in a nice interface. I can get all the stuff I want. And this is super common. Pop over here to the repository for dplyr, and I pop over to their pull request tab, and there's a bunch from today even. And you can browse them. You can see it points out we're merging into the main branch from this branch. We can look at all the changes they made, and there's even an interface for leaving review comments and saying, no, wait, don't do that. And you can put a comment in here. They provide all of these things for you. So you can, then the person could make new changes to fix your comments, push them. You could review it again, and so on. Now, let's talk about actually using Git in practice. Don't worry, there's a graphical interface. Just look for a Git extension or plugin or menu in whichever software you use. For instance, here is RStudio looking at the folder that we were just in, and I switched from environment to the Git tab, and it shows the current changes that have yet to be committed. I can tell it which one I want to stage, check the box. There's a little commit button. I can commit things. It pops up something, let me type in the message. So easy to work with without working in the command line if you so choose. So in the last few minutes, I'll mention one other thing, advanced bonus feature that comes out of, I suppose you don't need version control to do this, but it is now integrated into so many version control systems. That's usually how you use it, which is continuous integration. It's kind of a mysterious name, but the name is meant to reflect a principle, which is every commit you make should be a working version of the software. And each version should pass all the tests and checks you have. So if you've done unit tests, like you should, it should pass all the tests. If you have a style checker or something, it should pass all of those checks. And it should not be possible to accidentally put changes on the main branch that break the code. You should not be able to push code that doesn't work. If you are doing a system that automatically deploys the latest version of your code to the product when you push it, you don't want to be able to whoopsie push something and then break the system. And even if you're not deploying it live, you probably want to find out if you broke something. You don't want to break something and then only realize 2 weeks later when you try it. You want to find out as soon as you break it. So continuous integration refers to continuously running all of your integration tests. And it relies on there being a server somewhere, like say GitHub, that automatically runs a series of tests on every new commit or every new branch or whatever condition you set, and automatically reports errors and problems, and perhaps even refuses to let you merge things until you fix the problems. So this means your tests will always pass. You won't break things unintentionally. You can enforce style standards. And the same automatic system can do lots of other stuff. If you're making an R package, you can build all of the documentation and build the vignettes and make a website automatically during the continuous integration step. Or if your software needs an installer, you can automatically make the installer for the new version as soon as you've pushed it. Whatever it might be, even just making a website and deploying the latest version of the website when you change it, you can do that. That can be done with separate software. There's open source continuous integration software that works with Git and works with all kinds of systems. Or all of the Git platforms, the websites, will happily sell you products to do this. Many of which you can use for free on their educational plans. And they work using a special configuration file in your repository that says what you want it to do. In R, if you're like making an R package, the use this package can set that up for you automatically by setting up a simple workflow to, for instance, run your tests. For instance, this one. There's a special file in the repository. Actually, let me show you in the in our other repository for our R package, there's a hidden GitHub folder containing a workflows folder containing some files. This is one of those files. And it's the name of the workflow. It's defining when this should run. So on a push to the main branch or a pull request for the main branch. And it says run this job on a configuration, a matrix of operating systems, Ubuntu, Mac, Windows, using the latest R version. And it uses a set of predefined sort of actions that some R people sort of publicly shared, saying check out the code, set up R, set up the R dependencies, and then check the R package. And it'll run the unit tests, it'll run the R check functions. Um, and if it fails, it'll pop up a thing saying your change failed. And if it didn't fail, well, it'll pop up a thing saying it passed. So in fact, if I go back to this pull request from dplyr, you can see those checks are currently running, their checks. I'll check on this one from Ubuntu, and we can actually see what it's doing right now. It's building the package and installing it and checking that things work, and printing out messages as it goes. And if it fails, let's see if there's a recent one that failed. Aha, there's a little red X mark. If it failed, it'll mark, and hey, your code didn't work. You can click on it. Well, this is too old, doesn't have the error logs, but if it's a recent pull request, it'll show the log of what failed, and you can figure out what you broke and how to fix it. Actually, here's an example I had from our package where there were warning messages, and so it printed out and showed us, hey, your thing didn't work. So, what's the story of the Mori? Version control is a powerful tool, and Git can save you in a lot of ways, helping you go back in time, helping you collaborate, and in fact, essential for collaborative projects. So any corporate project you work on with a team will probably involve some kind of version control. If it doesn't, you probably don't want to be there. If it's like, it's the 90s, we just passed around floppy disks, it's fine. Probably an issue. Um, so try to get into using Git even on your own projects. That'll help you build some skills. And don't succumb to Git anxiety syndrome that my students have, where they did something wrong once and then they got confused. And so now they try to avoid doing anything in Git until the last possible minute, because that's not going to help you learn. I know weird things can happen in Git. I have plenty of stories, but the whole point of it storing the history is you can usually get back to something. If you did something wrong, you can usually go back. So don't worry too much about that. So I will leave you with a couple references. One to a Git book that's freely available online, one to a paper we wrote about our computing course where we teach Git, and one talking about using Git and GitHub for teaching intro statistics and how they did that in the classroom with intro students. All right, and I will stop there and see what questions we have. So I see one question about generating the git ignore file. And I will point you all to the package I referred to a couple times. Use this. It has all kinds of useful stuff in it, including you can have a thing, you can tell it to ignore files by running a function, or they have a function that by default puts in a certain set of things into the git ignore. So you just run that and it'll add it all to your git ignore automatically. They also have things like set up GitHub Actions to track your package. Actually, all kinds of stuff in here, set up continuous integration, set up your README, make a logo. all kinds of stuff in here for setting up code and packages and version control and so on. So let's see.
I do have a quick question.
Yeah.
Great presentation. I've never heard of Git Vaccinate. That's amazing. I'm glad I know that now. I always set up my own Git ignore files. One thing I was wondering is, do you ever use RStudio's incorporated GitHub where you just send in your hotkeys in your secret keys and then you set it from there? Because I found sometimes when I try and use it through RStudio versus either using GitHub or the terminal, that's where things get kind of tricky.
Yeah, and I guess I'll mention, if I come back to my repository. So especially with private repositories, well, anytime you push to a repository on GitHub, GitHub has to know who you are so that it knows that you can push to this repository. And there are a couple ways of authenticating. One, if I select to do it this way, that it'll use your username and password, which is annoying because then you have to deal with that every time or there's a special configuration. The other is using SSH and private keys, and you have to set up an SSH key and set that up on your computer, and then Git will use it. So there's a bit of configuration involved because you have to tell GitHub your public key, and then now it'll recognize you, and then you have to make sure RStudio and all your things use the private key, and you have to make sure you are pushing using this URL, not this URL. And if you get the wrong one, it'll ask for your password instead of using the private key or whatever. I have not had issues in RStudio using that, although I have not used RStudio. Well, allow me to show off for a moment. I use Emacs, and Emacs has Magit, which does all kinds of magic with Git, and it's much nicer than using any of the other things, other like Git interfaces. So that's what I usually use, and I don't have issues with it. But I think as long as you set up the public key on GitHub, it should work. I used to run into problems teaching students where like they set up the username and password on Windows and it got stored in some Windows password manager thing and you can never find it to figure out where to change it. And they changed their GitHub account to a different one and it's still using the old one and nonsense like that. But with SSH, I usually don't have those issues. Lori, I'll point out, you linked to the website there in the chat. They do have another version of that website, depending on your audience, called dangitgit.com, in case your audience doesn't, doesn't like that name, but they can choose, I guess. Any other questions about things?
I think I saw one in the chat that was asking about commit messages versus what's the difference between the commit message and trailers, and when do you use trailers?
I'm not sure what trailers refers to there.
I wonder if it's maybe the maybe sort of what you're elaborating on, sort of just underneath.
Well, I guess maybe I'll comment generally. There's commit messages, and then there's also comments in the code. So when you add something or change something, you could put a comment there saying this is necessary because reason. Or you can write a commit message saying this is necessary because reason. Or you can elaborate on other things, in a longer commit message. Or you can write a message in your pull request. So there's lots of different places you can write things. I typically use code comments to say what the code is doing, and maybe some details about the problems, like why I needed it to do this. I use commit messages to say why I made a change, sort of in the historical context. Oh, they changed the format and then they changed this, so here's what I have to do. And commit messages also get used as the communication when you are, for instance, sharing code with someone else. So you see the commits are shown here in the pull request. This person didn't write any message in their commit, but if they did, it would all be visible there. And people like those when they're reviewing to say, this commit does these things. Okay, now I'll read them and see what they did. This commit did these things, I'll read that. So I think you can think of it as writing for different audiences. The commit message is for your colleague you're working with, explaining why you're doing this. The code comments are sort of to explain the code itself, different purposes for different things. I see a question about LFS, which is a good one. So Git, because it tracks changes to files, it prefers text files. So it can, for instance, format a diff like this. But suppose you have a big file that is binary, a big data file or images or logos or whatever. When you make a change, all Git can do is just store a copy of the new one. And if you start making changes to data files, suddenly you're going to have hundreds and hundreds of megabytes or gigabytes of all the versions, the entire version of that. Whereas with changing a text file, Git can just store the changes and be much more efficient instead of storing multiple copies. So this becomes a problem because then you go to clone the repository or push it and it takes an hour because there's so many zillion huge files. So Git LFS is Git large file storage. And what it does is you get set up on a server that supports it, a separate place to store the large files. And then all Git does is instead of actually storing the file, it says, here's where the file is, go get it there. And if you change the file or whatever, that's fine. Git does not have to track it. It doesn't have to worry about, diffing some huge 500 megabyte file and all the complexity of it. It just has a file that's like I think 3 lines. Here's the version, and you can find it over here. And then if you need to update that large file, you can. So GitHub will have, I think, like 100 megabyte file limit. If you try to make a commit and push it with a 100 megabyte file, they'll tell you to stop. And they will provide you a certain amount of storage with Git LFS instead to avoid sort of blowing up your repository with a bunch of huge files. And I'll take the last question I see about working with branches. That is a change, like if you have a global thing across branches, can you have something that is the same on every branch when you change it? And I think the answer to that is no. You can't, for instance, have one file that stays the same across all branches. If you change it on one, it's changed on all of them. Because that, I guess the, physics nerd thing was that, that requires instantaneous communication between branches, but those might be on different computers with different people. So 2 people can make changes on different computers at the same time, and then you have to record those. What you can do is you can pick changes and transplant them. So if we go back to a diagram, if I have 2 parallel branches and I've made commits on one and commits on the other, I can cherry pick a commit and tell Git to apply it to the other branch. That is, by comparing the commit to the previous one, see what I changed. Now I go over to this other branch, the latest version there, and do those same changes. So that way, if you're working on one branch, you fix something in a file, and you want to make sure that fix is available on your other branch, you can do that as one commit and then cherry pick it to the other branch so that that fix will be available on both branches. But you can't have the file just sort of be a global file per se. All right.
Alex, well, thank you so much. It was a real pleasure to have you join us. I know that Donald and I will reach out to you for first slides, and we'll plan to have the recording available as well. Donald, you can maybe speak a little bit more to what we're able to add to Meetup, or if we can kind of email or message participants. What would you recommend?
Yeah, absolutely. We do technically have a YouTube and GitHub accounts, but I don't think we've ever actually used them for this purpose before yet. So this is kind of exciting. This will be a first timer. We'll also link those to the portal page for the website. So all those will be set up together. So well, once we get all that hosted, maybe we can send out a link so people can access everything.
Great. Excellent.